Hi, welcome to Unit 4, Day 10. This is Part 1, Polar Bonds and Molecules. We'll be doing an exploration in this lesson. So the purpose of the exploration are the following. There are three goals. In Part 1, we're going to learn what polar bonds and molecules are and how do we describe them with certain symbols. Part 2, we'll learn the difference between a polar bond and a molecule. Part 3, we're going to learn the importance of shape in determining a molecule's polar or nonpolar. The expectations for this lesson is that you must do the play posit, but you do have an option of trying the PhET exploration along with me. If you are going to do that, then you'll need to sort of flip back and forth between the PhET window and the play posit window. All right, so let's get started with some helpful background that will be useful for Part 1 and for the rest of this lesson. So first, we're going to define what polar means. You've probably heard the word polar before, like North Pole, South Pole, maybe polar bear, etc. The word polar means opposite. So North Pole and South Pole of the Earth, they're opposite poles on opposite ends of the Earth. In the case of molecules and bonds, when we say polar, they have a positive and negative end. So since positive and negative are opposites, if a molecule has a positive end and a negative end, they are going to have opposite ends. So that's what makes a bond or a molecule polar, essentially just has a positive and negative end. Now, how do we represent that exactly? There are three main ways that we show if a molecule or bond is polar. The first way is we use partial charges. Now, partial charges are these symbols that are shown here. And this sort of S-looking thing, that's a lowercase delta. So this is delta negative and this is delta positive. So if you have a partial negative charge, you'll be delta negative. And if you have a partial positive, you'll be delta positive. Now, what are these symbols represent? They're put over atoms in a molecular bond to show which end of the molecular bond is negative or positive. So if an atom has a partial negative charge near it, that means that that atom has a lot of electrons around it, and electrons are negative. So that means that that atom is in a negative environment. If it has a partial positive charge, that means that that atom doesn't have a lot of electrons around it. And so since the electrons are removed from its space, then it's a more positive environment. Doesn't mean that that does not mean that the atoms themselves are positively charged or negatively charged. It just means that their environment is. The second representation that we use are these arrows. They're known as bond dipoles, if you're looking at a bond, an individual bond, or molecular dipole, also known as a dipole moment for the entire molecule. So bond dipoles are the little arrows with like a sort of plus sign on one end, and the dipole moment is usually a bigger arrow with no plus sign. And in both cases, the arrow is going to point to the negative end of the bond or molecule. The second way is we use these colorful maps called electrostatic potential maps, and they basically color code the surface of the molecule. And typically, the color coding system works such that if that part of the molecule or bond is negative, it's going to be in red, and if it's positive, it's going to be in blue. Okay, so the next thing I want to talk to you about is electronegativity. And the reason why that's important is because polarity in molecules and bonds depend on the relative electronegativities of the atoms in the molecular bond. So remember, electronegativity is the ability of an atom to pull electrons towards itself in a covalent bond. And in the periodic table, the elements that are more electronegative are going to be found on the right, so where fluorine is, and then up, where fluorine is as well. So fluorine is actually the most electronegative element in the periodic table, followed by oxygen and nitrogen. Remember the noble gases, group 18, we don't measure their electronegativities because they don't form bonds. So that's just something to keep in mind. So anyway, so when we say more electronegative, what exactly do we mean? It's helpful to use this tug of war analogy. And here we have an image of a baby and a football player playing tug of war. So the rope that they're playing is representing actually the electrons in the bond. Now, who's going to pull the electrons closer toward it? It's going to be the football player, of course. And that's because you can think of electronegativity as strength. The football player is stronger, so the football player will pull the electrons closer toward itself. So the more electronegative atoms are sort of like the stronger atoms, and the less electronegative atoms are like the weaker ones. All right, so now we're going to get into our simulation. And remember, the purpose of the Part 1 simulation is to learn what polar bonds and molecules are, which we've kind of already went over, but you'll see that better in a simulation, and the symbols used to describe them. Now, the simulation that we're doing represents an individual bond or diatomic molecule. And di means two, so a diatomic molecule is a molecule with two atoms. For example, something like H2 or CO would be an example because that's a molecule that has two atoms in it. Whereas water, H2O, is not diatomic because it's made up of three atoms in total, one oxygen and two hydrogens. Now, when I say number of atoms, I'm talking about the total numbers, not the type, okay? So water has two types of atoms, oxygen and hydrogen, but it has a total of three atoms. So we're going to be focusing just on these diatomics, things with two atoms, or you can think of the simulation as representing a bond. And just a quick note, this is sort of like an FYI. Anyone who's planning on taking AP or college chemistry, there are some common diatomic elements that you ought to know, and I sort of highlighted where they're at in the periodic table. So H2, N2, O2, F2, Cl2, Br2, I2. We're not going to necessarily be tested on that here, but since it's related to what we're talking about, I just put that here. All right. So let's go ahead and go to the PhET link. Remember, you can do this along with me because the PhET link is linked in your folder if you would like. If you do want to do that, you want to pause it, open up that link. Okay, so let's get started. We're going to do the two atoms. That's our part one simulation. And what you may notice is that you have two atoms here, which can again represent a diatomic molecule or a single bond, atoms A and B. And you also notice that they have their electronegativities written at the bottom, A and B, and it's sort of like on a scale. Now, there's ways that we can sort of view it. Right now, the bond dipole is highlighted. So we're going to also highlight the partial charges and the electrostatic potential, because those are the ways that we show we can, we talked about that, we can show if a molecule or bond is polar or nonpolar. All right, now that we've had those things highlighted, I want you to take a look at this molecule and think back to your definition of a polar molecule. A polar molecule has a positive and negative end. Based on what you see here, do you think this molecule is polar or not? Great, so it is a polar molecule. It has a positive end, which is over where atom A is, and you can tell that because it has that partial positive charge there, and it has a negative end, which is where the atom B is because it has a partial negative. You can also tell from the potential map because the positive will be sort of surrounded by blue halo, and then the negative side will be surrounded by a red halo, which is what we see. You can also tell because there's a bond dipole, and bond dipoles only exist when you have a polar bond, and in this case is pointing towards atom B. Okay, so let's now relate that to electronegativities. You see their electronegativities at the bottom. What I want you to think about is which atom will have the partial negative charge. Is it the atom that is more electronegative or less electronegative? So use the information that you see here. Great. The atom that is more electronegative, atom B, has the partial negative charge. So let's think about why that is. Remember, they're sort of like playing tug of war, these two atoms. And atom B, being more electronegative, is stronger. So it's going to pull the electrons closer toward it. If the electrons are closer toward atom B, that means that atom B is surrounded by a more negative environment, okay? And so that's where that partial negative charge is. On the flip side, atom A sort of lost some of those electrons, right? It didn't lose them completely, but the electrons were moved away from it. So since those electrons were moved away from atom A, its environment is positive because electrons are negative. So if you lose electrons, you're going to become more positive. Okay, now let's play around with this a little bit more. Right now, atom A, its electronegativity is on this less scale, so it's the lowest that it can go for this simulation. And atom B, its electronegativity is in the middle. So what do you think will happen if we made atom B have the same electronegativity as atom A? Basically, we take this scale and move it all the way to the left. So I want you to pause and think about what do you think will happen? All right, let's take a look at that. Let's see. Notice what's happening to the bond dipole and the partial charges. They're getting smaller, right? And also look at the electrostatic potential map. starting to fade. And when I bring it all the way to the same level as atom A, so now atom A and B have the same electronegativity, they're equally strong. The colors in the electrostatic potential map have disappeared. My bond dipole has disappeared, and my partial charges have disappeared. So what do you think that tell you about this molecule? When atom A and B have the same electronegativities, is it polar or nonpolar? Great, we're dealing with a nonpolar molecule here. So, and we know that because there's no positive or negative side. So that's one thing that's key about what makes something polar or nonpolar has to do with this difference in electronegativity. If there's no difference, if they're equally strong, there won't be a positive or negative side. The molecular bond will not be polar. Now let's go ahead and set that back to where we had it, where atom B its electronegativity was in the middle. What if we made atom B, I mean, it's stronger than atom A right now, but what if we made it much more stronger by moving it all the way to the right? What do you think will happen? All right, now notice what's happening as we do that. The bond dipole is getting stronger, larger. The partial positive and negative charges are getting larger. So, sorry about that. So as I said, when we make atom B much more electronegative than atom A, it becomes more polar, and we can tell that because the partial dipoles are getting bigger, the bond dipole is longer, and the colors of the electrostatic potential map are much deeper. So let's sort of summarize some of the things that we've covered here. So the main thing is the difference in electronegativity determines if a bond is polar or nonpolar. Nonpolar bonds or diatomic molecules, they share the electrons more equally, so there won't be a positive or negative side. However, in a polar molecule or bond, they don't share the electrons equally, and so the less electronegative atom becomes partial positive. That should say positive, by the way. And the more electronegative atom, the stronger one, becomes partial negative. So this should say partial positive. And the other thing to note is that the greater the difference in their strength or electronegativity, the more polar the bond becomes. And we can sort of represent that sort of on this spectrum arrow here. So when the difference in electronegativity is small between, let's say, 0 and 0.3, that's a nonpolar covalent molecule. Not a lot of difference in electronegativity, so they're sharing it roughly equally. But as if the difference in electronegativity between the two atoms is between 0.3 and 1.9, we've got a polar bond, and it becomes more polar as it gets closer to the 1.9. Now, what if we have a case where one atom is much more electronegative than the other? So much so that it actually rips the electrons out of its hand. So that's sort of what we've got going on when we talk about ionic bonds. So let's say atom A and B they're pulling, but atom B is so much more stronger than atom A that it takes the electrons away. Well, then that would make atom A positive because it actually lost the electron, so it has a complete positive charge, and atom B will be negative. And that's what happens in an ionic bond. The metals will lose the electrons and get a positive charge because they're so much less electronegative than the nonmetals, which will gain the electron and get a negative charge. So if we go back to this idea of this scale here, if the difference in electronegativity is greater than 1.9, then we have an ionic bond. So if it's higher than 1.9, then it's an ionic bond because their difference is so great that the nonmetal rips the electrons away, becomes completely negative, and the metal loses that electron and becomes positive. So here are some key takeaways from part one. One is that polar bonds and molecules have a positive and negative side, and that can be shown with partial positive and negative charge symbols, the dipole arrows, or colorful electrostatic maps. Now, bonds are polar if the two atoms in the bond have a significant difference in electronegativity, so significant differences in their strength. The greater the difference in their electronegativity, the more polar the bond. And if the difference in electronegativity is really, really large, then it becomes an ionic bond because one atom will just rip the electrons away from the other. All right, so that is it for part one. Have a quality day.